Line 22, 7b97z82, OH reactive molecules, magnetic 4 transitions, quantum transport, 5G Wow Seti. There's the alien radio signal. And this is about highly reactive OH radicals, 4 transition frequencies in outer space, keyword research. September 19, 2013. The previous video was line 22, 7b97z81, Nonadiabatic, Landau-Zener tunneling, Fe8 molecular nanomagnets, 5G Wow Seti. So I'm going to Google the atomic pulse equations for the keywords. And quotes and PDF file results were on a blog. Optical dipole force on ladder-like 3-level atomic systems driven by chirped fused cycle pulse laser fields. There's the name of the scientist, June 2012. The link is arxiv.org. I googled optical dipole force, a quote from the blog, direct cooling of ground state molecules. In 2002, our group began cooling studies of highly reactive OH radicals with the goals of making precision measurements of 4 specific transition frequencies that have different dependencies on the fine structure constant. A. The hope was the precise laboratory measurements could then be compared to observations of similar OH transitions in outer space that took place billions of years ago in the early universe, but which were only recently detected on Earth. Provided both astronomers and laboratory scientists could measure at least 2 of the 4 transitions precisely enough to detect small differences in A, the value of A today could be compared with its value 10 billion years ago. This allows a test for various extensions to the standard model. Our group succeeded in making this measurement by using a Stark decelerator. Invented by G. Mellier's group and developed for OH in the GLA lab in 2003 to put the brakes on fast-moving OH molecules until they traveled sufficiently slowly through a microwave measurement cavity. The Stark decelerator could slow these interesting dipolar molecules to lukewarm temperatures of about 50 mK. So here's a magneto-electric trap used to confine OH molecules at 30 mK. The high current coils, blue, apply a magnetic quadruple trapping field, while the surrounding electrodes, red, allow for the application of electric fields to the trapped OH sample. From the very beginning, our group has focused on the possibility of trapping OH molecules in a magnetic trap and leaving the external electric field freely available to tune possible molecular interactions. This has turned out to be a very fruitful scientific direction. First, we developed a Magneto-electrostatic trap for studying cold collisions. In the process, we optimized the Stark decelerator to produce molecules moving slowly enough to trap. Then we coupled the end of the accelerator into a magnetic trap surrounded by electrodes capable of creating both uniform and non-uniform electric fields. In studies of the new trap, we discovered that an applied electric field not only affected the number of molecules trapped, but also modified the trap itself, making it deeper so fewer molecules could escape. The electric field also changed the oscillation frequency of the OH molecules inside the trap. To enhance the spatial density of trapped molecules, we then invented a permanent magnetic trap that is perfectly mode-matched to the Stark decelerator. And the link is gila.colorado.edu. This allowed 50% of the entire decelerated molecular packet to be loaded and trapped in the magnetic trap. Atomic pulse equations and its form is going to continue in the next 20 or so videos. Okay? Sorry, I had to speed that up. The battery was running out of power here. Thanks for watching.